In this video, we're going to look at how Thales used the geometric proposition to find the height of the pyramid. So the black triangle here represents the pyramid, and I also draw a right triangle right here. So the vertical line, the height, you can imagine it as a stick, a post, or staff. So this one right here, and what we're going to do is we're going to draw the height of this pyramid. So from here to here. So that means this is also a right triangle right here. And we're gonna look at the shadow under the sun, and we draw the shadow of the top. We found the top. Start from the top, and we get the shadow, and then we draw the horizontal to the ground. Okay, so the red triangle is also, we draw here, they're both right triangles. This is a right angle, and that's also right angle because they both represent height. And you can think of this as a stick. You put it on the ground, and the shadow under the sun, this hypotenuse side, the longest side of this right triangle, that's the shadow. I'm sorry, the shadow is on the ground. So the shadow side, we're gonna call it S on the ground, and but we join from the top of the stick to the top of the end of the shadow, and join them to make a right triangle. Similarly, from the top of the pyramid to the end of the shadow, and then we join them, and that's how we got these two right triangles. And the geometric proposition is, if you have two similar triangles, and these two triangles here, they are similar. And how we know they are similar, one of the properties we can use is if these two, the assumption right here, these two triangles are similar because they're both under the sun, and they should form the same angle right here and here, and they have a 90-degree angle, which means these two angles are also the same, because a triangle has 180 degrees. So subtract 90 degrees, so the other two angles should add up to 90. And the same here. And if they have the same angle, same angle here, then the other angle should also be the same. Okay, so now we want to use the proportionality to find the height of the pyramid. So the length of the stick, we use h prime to represent it. If you have two similar triangles, the corresponding sides are going to be proportional. So let's look at these two triangles. The corresponding side, the height h corresponds to the height h prime, and the shadow s of the pyramid corresponds to, from the top to the starting from the height, should be correspond to the other side of the triangle, the shadow of the stick. And we have another hypotenuse side. In this case, we don't really need the third side. If we give it a name, a hypotenuse, or let's call it maybe C, and this one C prime. C corresponds C prime. But in this case, we're just going to use these two here. So the proportion we're going to form will be h over h prime. Two heights is going to be, the ratio of two heights should be the same as the ratio of these two shadows, straight sides. And if you want to add one more, you should also get the longest sides should also be proportional. But again, we're not going to use these when you just try to find the height. Okay, now we do cross multiply because this is a proportion. One of the properties we learn in the elementary math class is when you cross multiply, they should be equal to each other. Okay, and this is a different way to write the proportion. Instead of in the fractional form, we have multiplication on both sides. And what we're looking for is h. So if we know, for example, in the case, if we know that the height of the stick is 6 feet, and the shadow measures 9 feet, and we can also measure the shadow for the pyramid. That's 700 from here to here, 720, and we can plug everything into this equation and solve for h prime. So h will still be h. S prime is 9, and s prime is 9, and h prime is 6, and s, the shadow of the pyramid, is 720. And now we can use algebra to solve this. H equals 6 times 720 divided by 9, and if we simplify that, we can get 480 feet. So that's the height of this pyramid. So we try to prove the Pythagorean theorem. You can use the proportions when you try to find the two similar triangles. And how do we prove two triangles are similar? We need to make sure one of the properties we can use when you have two just arbitrary triangles. Well, in this case, we have two right triangles. When we have two right triangles, it'd be easier. So, for example, if we look at the case of right triangles, this is a right angle, and then we draw another height here, and you can look at this triangle, and with the biggest triangle, they should be similar, because how do you prove it? You're going to prove that by angle property that you may have learned in algebra class. And if they have these two triangles, the largest triangle with this shaded triangle, they should have 3 equal angles. One straight angle, 90 degrees, plus they share an angle right here, and that makes the third angles equal. This one should be equal to that. So you can prove this easily. So once you can prove this big triangle and the shaded triangle, they are similar, and you can use the proportion of the corresponding sides. And when you do that, you can maybe use some letters. For example, we know this side is C, but what is this side? You can use a letter, for example, X, to represent it, which makes this side C minus X, because when you have C, cut X off, then you have C minus X. And similarly, you might be able to also prove this triangle is also similar to the big triangle. So you may have two proportions, and you can use algebra skills to get something like this, and you might be able to plug in and prove that the Pythagorean theorem. So that's a little bit of hint for a proof of Pythagorean theorem.